Here is the question that I ended the last part of this lecture with, and all you needed to realize was that because the ball is slowing down, as we've seen, anytime an object is moving in a straight line and slowing down, its acceleration points in the opposite direction to the motion, and so the acceleration vector points down. That rule, if you want to think of it that way, that the acceleration is opposite the direction of motion for an object slowing down, is all you need here. But let's just review what the reasoning is. So if I think about the moment at 0.2 seconds, I could think of this vector just before it as an initial velocity and this vector just after it as a final velocity. And let me just pull them out over here. And then I need to do Vf minus Vi, so I'll flip Vi to get negative Vi and move it over and carry out the vector subtraction, and I see that delta V is down. If you answered up, you may simply be confusing velocity with acceleration. The velocity tells you which way the object is going, and this object is certainly going up, but the acceleration is all about how the velocity is changing, and it turns out to be down. As long as we're at it, I'll just quietly remind you of something that I might have mentioned before. Vectors cannot be positive or negative, and there's no such direction as negative. As I hope you're getting used to, the vectors, by which I really mean the arrows, do not depend on our coordinate system, and so I haven't defined coordinates. But if we wanted to talk about the components of these vectors, now we would have to define a coordinate system. So if we took a fairly typical coordinate system like so, then we would say for this car speeding up, its x component of acceleration would be positive, whereas for this one slowing down, its x component of acceleration would be negative. But there's nothing sacred about speeding up being a positive component of acceleration versus slowing down being a negative. Because if instead I define my x-axis pointing the opposite way, now the x component of this acceleration is negative, even though this is speeding up. And the x component here is positive, even though this is slowing down. So many students have a misconception about a positive acceleration meaning speeding up and a negative meaning slowing down that I think I'd better clarify this further. First of all, remember, acceleration is a vector. It doesn't even make sense to talk about it as positive or negative, but you can talk about its components as positive or negative. What we can say is that when something is speeding up, its acceleration and velocity vectors point in the same direction. And when it's slowing down, its acceleration and velocity vectors point in opposite directions. We can't talk about components, though, until we define axes. If we define axes the way I have here, then for the car speeding up, its x component of velocity is positive, and its x component of acceleration is also positive. Whereas when it's slowing down with these axes, its vx is positive and its ax is negative. On the other hand, if I flip the axes around, all those signs change. What we can now say in terms of the signs of the components is that for an object speeding up, moving along the x-axis, the x components of its acceleration and velocity have the same sign. And if it's slowing down, the x components of acceleration and velocity have opposite sign. From now on, we are always going to include acceleration vectors on motion diagrams. And the reason is that really the main reason we draw motion diagrams in the first place is that they help us to think about the direction of acceleration, which we often need to know. What I mean by always include them is that we're going to draw the acceleration vector next to each point on the diagram, except as we'll see for the points on the ends. Let me show you an example of the process of adding acceleration vectors to a motion diagram. So here we have a motion diagram, and if you look at it, I hope you notice that there's an initial part where this object is speeding up, a middle part where it looks like it's going at constant speed, and an end part where it's slowing down. I'm going to show you the reasoning for one point. I'll pick this point. So I'm going to take the velocity vector just before it as an initial v and the velocity vector just after it as a final v. And I'm going to use them to get an acceleration. And we've seen before the process of vector subtraction that we use to go through this, and it tells us that the acceleration is in the direction of motion. The object is speeding up, and so the acceleration is in the direction of motion. And now we can just repeat that for all the other places where we see that it's speeding up. What about the first point? Well, we don't know the velocity just before the first point, and so we can't put an acceleration vector there, and that's why I say that we'll add an acceleration next to each point except at the ends. Now let's move on to the middle part. So here, these velocity vectors are the same, and so the delta v is 0. They subtract to give 0. We could just leave it blank, and many people do, but I'm going to say it's clearer to write a 0 above each place where you come up with a 0 acceleration. And now we'll just do the last part. And again, we've seen what happens when an object moving in a straight line is slowing down. The vector subtraction looks like this, and we get an acceleration pointing opposite to the direction of motion. And that will carry through for all of the other places where it's slowing down, at which point we have now fully labeled it. And if you are in practice doing this, you could probably add all these acceleration vectors to this motion diagram in a matter of 5 or 10 seconds. This is a key skill, and so let's make sure that you've understood the process. So I've provided you here with a motion diagram which needs to have its acceleration vectors added, and just note that this is one of these cases like we saw in the previous unit where the object is reversing its motion in the middle. And so to avoid the confusion of having the motion diagram run back over itself, the part after the change in direction has been offset. In any case, choose which of the options below have the correct acceleration vectors.